So yesterday we spent a lot of time going through all these examples of self-similar Markov processes, positive ones, and they were all built from the stable process. And Osvaldo gave some nice calculations in the afternoon. So today I think we looked at this, right? I think we did all this. Wow, I think I'm going to finish early. Okay. Today we're going to do a calculation. Come on. Which is this guy here. So this is the stable process killed on exiting the half line, and as Osvaldo showed us yesterday, so the trick is to write this as this indicators with the first passage time, which is actually really, I can really write this as in this way. And so you can see it's a Markov process. And the self-similarity, because again, the pair were self-similar, so it's a functional of the pair. And so we're going to try and work out this psi star. And remember, being a positive self-similar Markov process, it necessarily has a form which looks like this. So this guy, we're going to try and work it out. And we already said yesterday that you can predict that the Levy process must have a killing, because the stable, this being a stable killed on first passage below the origin, the factorization, the two factors, the two Wiener Hop factors were like this. This is the descending Wiener Hop factor. So if you think about the range of this process, so forget the time change. The range has nothing to do with what speed we sample the Levy process at. It's just the exponential of psi. So the new minima associated with this process will be the exponential of the descending ladder of this process. And because the descending ladder process, of this process, not of psi, of this process, there are two Levy processes. Here is a stable, and here is the Lamperti stable. So if we look at the descending ladder of this guy, all right, so because it's a stable subordinator, it has no drift, right? So in the range going down, it will, with probability 0, not include the origin, and therefore this guy is going to jump over the origin when it passes below it for the first time. So it means that in this representation here, this thing has to have a killing. It has to suddenly drop to 0. The indicator will then keep it at 0. So this has to have a killing term in it. So the first thing we're going to do is say, let's look at, let's imagine we are at a certain point in the evolution of this self-similar Markov process, xt minus. So we've just approached time t, and a jump is occurring. So the jump is going to occur with this rate. Okay, so it's going to jump somewhere with this rate. And so it's going to jump and get killed with this rate. So this z star is what I'm defining for the whole thing. So this is, I'm just approaching time t, and I'm saying a jump is going to arrive. So what's the rate of arrival that will take me into killing? So I'm at this height z star t left limit. I know the rate at which I jump in general is this, so I need to be jumping greater in a negative direction, greater than that distance. and that would kill me. Well, so apart from the constant, that's an easy integral. It comes out looking like this. So on the one hand, we can say at any t, the rate at which I jump and get killed looks like this, and that's just an integral coming from the general jump rate of the levy. Now, on the other hand, if I look at the representation, which I know must necessarily hold, and I also necessarily know that this has a clock, so the clock of this psi without the time change is ringing at rate q star. So when I put the time change in, it's ringing at rate q star phi prime. Okay, so phi prime, you remember, phi is the inverse of the integrated exponential. So with this being a continuous quantity, this in particular implies this equality holds. So if I differentiate this, it doesn't matter that it's random, it's differentiable, it tells me that phi prime e to the alpha psi phi t is equal to 1. So it gives me an identity for the rate of change of phi, which I've plugged in here. Okay, so just flip this on the other side. But of course I recognize that quantity is itself just z again. Okay, so in a little dt, on the one hand from this representation, a jump will kill me with this rate. On the other hand, with this representation, a jump with the Lamperti representation, a jump will kill me with this rate. Now, of course, I've got a t left limit here and a t, but it doesn't matter because it's measured against Lebesgue measure, so it's integrated against Lebesgue measure in some sense. So if I make the comparison between those two, well, it gives me immediately an identity for the killing rate. Right, so I've used here the reflection formula for gamma functions, just to tidy that up a bit. So already we're kind of in a nice place now, because we've said I'm trying to find this Laplace exponent of this guy psi, and it's got killing. So by the generalized Levy-Hindchin formula, I know it starts with a q star, and then there's some Levy-Hindchin bit that I need to work out next. Okay, so I've already got the q star. Okay, so how am I going to get the rest of the Levy-Hindchin? So now I'm going to look at the left limit of this killed stable of z star just before it dies. So exactly here. So this is not included here because it's CAD lag. Okay, so I'm just going to look at that last position just before it dies. Well, of course, this is just the same as the position of the stable process just before it jumps below the origin by the definition of z star, which is what I've written there. Now, what is that position in terms of psi star? Well, it should be wherever psi star is at the last moment of phi before it dies. But I don't need to worry about how this phi, what this phi is at zeta left limit, so that's what I've written there, just before it dies. I mean, I know when it dies when the exponential clock of Xi star rings. So however that translates through phi doesn't really matter. The only thing that matters is that time at zeta, phi of zeta, is the exponential clock ringing as far as Xi star is concerned. So this pre-death position is exactly e to the Xi star sampled at this exponential with the rate that we've just worked out. Okay, so now I look at the Mellin transform of this position just before death. I'm going to start from 1 that's a convenience. Starting from 1 is equivalent to Xi starting at 0. Okay, so what I'm doing in the end because of scaling shouldn't really matter where I start from, so I'll just pick a convenient one. This is the Fourier transform of Xi star at the exponential clock. So it's almost the Levy-Hindchin formula, right? So what it is, if I just do the math here, so let's call this the residual. Well, the residual is, this is almost a non-statement here, is that, right? What I get when I subtract Q star. So if I look at the Fourier transform of Xi star, it's e to the this times t. Now I'm going to randomize this with an exponential with rate Q star. Okay, so I need to randomize this accordingly. Okay, now let's be careful. This is complex valued, this phi, but I'm going to treat it as a real valued object. Trust me, it all works out. You need to look at the real part of this psi to be sure, but this calculation is safe. It's for all Levy processes the case. So I get a Q star from here, and then nicely this combines with this Q star here, so this is minus makes a plus, kills that one. So I end up with 1 over psi star theta. So what this tells me in the end is the Mellin transform of my pre-death position, which is the Mellin transform of the stable just before passing below the origin, is exactly Q star over psi star. So, okay. So now we go to my book, which you've all read, and you all have illegal copies of, and if you don't, I can supply you with one. And you look at some exercise at the back of chapter 8, and you say, hang on, this guy's already worked this out. So actually not me, but Zolotarev had worked this out in the 70s. So the joint law of, not even some Russian anyway. So this had been worked out, I think, even in the 60s. It's basically, it was Rogozin. But there is a formula for this. It's been well known for a long time. What I've done here is I flipped the problem around, and I've said, starting at 1, where's my position immediately passing below 0, is the same as the dual, so that's the negative of the stable. So just flip the roles of rho and rho hat, exchange their responsibilities. That's the same as starting at 0 and looking at the position just before I pass 1. So the position just below 1, or the relative position to 1, just before I pass. So that simply is to get me ready to use Rogozin's identity as it's written in my book, I think. Plug it in. So in fact, you see here a triple integral. So really what's going on here is this density is the triple law of the overshoot at 1, the undershoot of the position just before jumping over 1, and the undershoot of the last maximum. That's actually the real identity that's going on there. So we've fixed the whole thing so it's x hat passing 1. So it has a kind of nearest pass. This is x bar at the left limit. This position is x at the left limit, and this is x at the jump time. So this triple here is known, and I've just remembered it's not Rogozin who proved that triple, is me, with Juan Carlos and Victor. And that's what this is, this density here. So we need to integrate 2 out of the 3 to get the one I'm interested in, which is this one here. Okay, so it's a little bit delicate, this integral, because it's it's kind of a hypergeometric integral and then a beta integral. So one needs to be a little bit familiar with those things, but actually I found there's enough info on Wikipedia on hypergeometric functions to sort this out. So it's done there for you, and it comes out with a whole load of gamma functions. So there's also a lot of cancellation going on here with some of these gamma functions. And I think here the tricky bit is making a change of variables, which I've indicated here, which might be very useful for you later. So this is a good exercise to just run through this calculation once. Okay, so after all the cancellation here, remembering the answer is q star over psi star, and remembering I have an explicit identity for q star, I can just rearrange all this mess and it gives me the psi star, and there it is. It comes out as a hypergeometric Levy process. Okay, so that was shock number 1. Unbelievable that you get such a nice Levy process, and also remarkable that it falls into this very nice class of hypergeometric, but also a little bit inevitable somehow, because so why is it that we necessarily get a nice Wiener-Hopf factorization here? Well, somehow it must be an inevitable consequence of the fact that the range, if you think about what Wiener-Hopf factorization means, it's telling us something about the range of the descending ladder and the range of the ascending ladder of this weird thing, right? Because forget the exponential, I mean the range is just exponentiated, and this time change has nothing to do with range, right? The places you visit is a different story to when you visit them. But this is fundamentally a stable, right? So the range of the maxima of this thing is the range of the maxima of a stable until it passes below the origin, and we know a lot about the range of the maxima of this thing. It's hidden in this very nice Wiener-Hopf factorization here. So in a sense, a posteriori, it's not massively surprising, but you would still never guess it, that you do get an explicit identity with a Wiener-Hopf factorization. I suppose the thing I'm referring to is with a Wiener-Hopf factorization. Okay, so here is my big problem, one of my 2 big problems for this week, which I know you can solve, and Cecile knows this can be solved because she's worked on it secretly. Right? So this was actually something I have to give credit to Tim Budd for this. So Tim Budd is a physicist from Nijmegen in the Netherlands, and he's worked with all these planar map guys, Nicolas Curian and all these maniacs. And he told me about this, that he's seen this in his calculations before. So I went and checked this out with a student back home. So I know this is doable. This is another path transformation of a stable process. So it's the one where it's almost the same as the one we've just discussed. So you run your stable, and eventually it will jump below the origin, right? Now when it jumps below the origin, if I call this quantity delta, I'm going to add 2 delta to this point here. So this is a positive quantity here, so I'm going to basically shunt it up here. And more generally, I want to ask what happens if I shunt it up not by 2 delta, but maybe 3 delta or 4 delta or 5 delta, and then carry on as before. When it drops, shunt it up. So in a sense, just reflect it over. If it's 2 delta, it's kind of you just map it back up and carry on. Map it back up and carry on. So, the questions for Friday are, how can you write this as a path transformation, as an endogenous path transformation of the stable path? So omega for omega, how can I write this as a functional transformation of x? So this is a functional transformation of x. What is the right functional transformation for this shunted process? Is it self-similar? Of course, yeah, it's a rhetorical question. Of course it is. It should be. So prove it. And what's the underlying Levy process? Calculate the underlying Levy process. So this should be, you should get a very nice exponent for the underlying Levy process. And the one and only hint I'm going to give you here is this story and this story are kind of similar, right? So until the first passage below the origin, they're more or less doing the same thing. So there's some learning exercise here which tells you at least how to kickstart this this process, this shunted process. So until you first pass below that, they're doing the same thing. Okay? So that should tell you something about the xi in here already. Right? Because until this passes below the origin, it's behaving like a Levy process, e to the Levy process time change. It's just the killing that's sending it to this guy to minus infinity. So the same is here, except we're not sending it to minus infinity, we're resurrecting it somewhere else. Okay? I've practically solved it for you. So solutions on Friday, please. I'm not going to do the solution for you. Please try to make the effort to prepare something for Friday. Okay, so that was my first big problem. It's on the slides. The slides are on the web page. Now I'm going to carry on, and I'm going to go back to the processes we looked at, which we'd identified as self-similar Markov processes, and let's find their Levy processes as well. Okay, so more learning exercise for your problem. Let's look at some of the other ones. So this was one of the cases in point. This was the stable process conditioned to avoid the origin. It is a dupe H transform of the stable process killed on going negative. The H function is x to the alpha rho. Or if you like, this is a martingale change of measure. Well, now we know this identity here. We can just plug it in here. This is nice because it looks like this thing just raised to the power alpha rho hat. So all I'm really doing here is taking an e to the alpha rho hat psi star, and then the indicator that the clock didn't ring yet for the Levy process. Now, if I go back to this, let me keep this up on the board here. How have I stated it? Z. other way around, alpha minus iz, 1 plus iz. And on the bottom is gamma alpha rho hat. And gamma 1 minus alpha rho hat. Okay, so let me convert this to a Laplace exponent. So you remember this thing comes from e to the iz xt. So if I make the transformation z maps to minus iz and psi, well, I don't need to, I can put a negative on the psi to make it a Laplace exponent. It's not so important. But this is the transformation that will make this a Laplace exponent if it exists, because the moment generating function of a variable is not guaranteed to exist. But let me just do it brainlessly. So the Laplace version is gamma. So last time I checked, minus I times I is 1. So when I plug this in here, I should get alpha minus z gamma 1 plus z over gamma alpha rho hat minus z gamma 1 minus alpha rho hat plus z. Okay, so this is in Laplace form. And actually, Mariana was mentioning this yesterday. Moment generating functions, when they exist, are nice and convex. So this is a nice convex function. And you can see already where it has problems. So the gamma function explodes on 0 and then the negative integers. So it's a nice function except the negative integers and 0. So we've got a problem at alpha and a problem at minus 1. And we have not a problem, but a root. So this thing exploding or this exploding is actually quite nice because it gives us a root. So it says we've got a root at alpha rho hat and another root at alpha rho hat minus 1. So this Laplace exponent of psi star, so rather than the Levy-Hinchin, a Laplace version of the Levy-Hinchin looks like this. So somehow it's exploding at, where did we say, alpha and minus 1, and it has a root here at alpha rho hat and a root here at alpha rho hat minus 1. And 0 must be here somewhere. Okay? So it's a pretty nice Laplace exponent. So let's go back to what we were doing before, and we look at this and say, well, this condition to stay positive is just a H transform. But in the language of the Lamperti transform, it looks like an exponential change of measure. Right? So of course, you all know Girsanov's theorem, which says that if you take a Brownian motion and you raise it to the power, you raise it to an exponent, sorry, you exponentiate it. So you remember this one is a martingale, and if I make a change of measure with this, what happens, so B under the P sigma is a Brownian motion plus drift, sigma. Well, something similar happens with Levy processes, providing you have moment generating functions. So in general, for a Levy process, so providing psi of C exists, there exists psi of C, And remember, I talked about Laplace exponent. So for me, a Laplace exponent looks like this when it exists. So now this is a martingale. And this change of measure has the property that under the change of measure, it's still a Levy process. And its Laplace exponent let's call it psi c theta, is just the Escher transform of psi. So it's just a shift in the argument of psi. So this looks like this exponential change of measure. The problem is I seem to be missing the Laplace exponent times t. But remember, there's something special about the number alpha rho. It's a root, alpha rho hat, sorry. So if I took this martingale at c is alpha rho hat, this thing is 0. So this really is the Escher martingale. This is the exponential change of measure. Okay, I'm sampling it at a stopping time, which is this phi. But if you think about it, phi is the inverse of an integrated clock, integrated exponential Levy clock. So it's a stopping time. So really, at the end of the day, since this is just an Escher transform of the underlying Levy process, I know what the characteristic exponent of the Levy process hiding behind this condition stable is. It's just the Escher transform of psi star. So all I do is I shift the origin here. Okay, so I subtract alpha rho hat from everything here. So alpha minus alpha rho hat is alpha rho, because rho and rho hat add up to 1. Here I've got the 1 plus alpha rho hat, so I'm shifting z, let's say, by alpha rho hat. So I add it here and subtract it here. Here I get rid of this, here I add and get 1. And again, you can see that my roots and poles are all in the right place. I've just shifted the origin here. Okay, so this is the exponent now, another hypergeometric Levy process, which if you put it in this context doesn't seem a big surprise that it's another hypergeometric process of the stable conditioned to stay positive. So there's another root here. So the question you immediately want to ask me, of course, is what would happen if you Escher transformed to this root here? So there is another exponential martingale, which I can build by taking the constant c to be this root. So that would kill this thing here. And if I did that, that would appear to be the equivalent, remembering that x indicate at minimum is positive, is e to the psi phi. So if I took the root here, alpha rho hat minus 1, that's raising this to the power alpha rho hat minus 1. Stopping time doesn't matter. This 0, this root here is making this the correct martingale. So this appears to be also an appropriate Dubh transform. And in fact, you can, so it would move me to this Laplace exponent, so shifting the origin here. So now I'll go the other way, and I'll say, what is the self-similar Markov process with this exponent? So arguing as before, it appears that I'm saying I'm just performing an Escher transform with this exponential martingale, which is equivalent when you plug in the stopping time to this martingale at the level of x, the stable process at the time scale of x. Here I'm saying, here, remember the gradient of the exponent tells us, at 0, tells us the drift. So when I've moved my origin here, I get a positive gradient. So the self-similar, the stable process conditioned to stay positive. Obviously, the underlying Levy process likes to go upwards, likes to have a positive drift. Putting the origin here, I get a negative gradient. So whatever self-similar Markov process I create here, moving the psi here, it's going to like to go down to minus infinity. So thinking again of the Lamperti transform, once I've Escher transformed here, this guy is going to like to go to minus infinity. So this thing is going to be attracted towards this x. The resulting change of measure should be something attracted towards the origin. And in fact, it turns out that this is the Doob-H transform of, I haven't said it here, but it's the Doob-H transform of a stable process conditioned to absorb continuously at the origin. So conditioned to limit to the origin in a finite time. So I'm suggesting here you check this is a self-similar Markov process. Again, it's just because the scaling passes through this Doob-H transform rather nicely because of the polynomial form. Right? So I need to multiply by c on top and bottom, and that only works because of the polynomial form of this. If this was any other function of xt, multiplying xt by c wouldn't necessarily allow me to multiply the starting position by c. So there's something magical here about being a polynomial, but that, of course, is because it's an Escher transform, because it's an exponential martingale. Okay, another example, and then I'll finish. Yeah.
How can I read from the H transform, from that formula, that it's conditioned to constantly?
Yeah, you can't. The only thing you can read is that this transformation is mapping me to a Levy process with origin here, and therefore a Levy process that likes to go down to 0, to minus infinity. And since x, under this Doob-H transform, and x, the self-similar Markov process associated to that is still, if this is the law of or the process with the law of the Levy process with origin here, this is still, you've changed what was this under this Doob-H transform has changed to that, right? So psi star is this exponent, and psi down arrow is the exponent where the origin is here. So, of course, it's still a self-similar Markov process. It keeps the same shape. It's still a Levy process, but one that goes to 0. So all I can say is it's a self-similar Markov process that attracts to 0. There's no killing here. It's 0 at 0, psi at 0 is 0 at 0, so there's no killing term. Here it's, the Q is there. And the fact that it's the condition process is a thing I'm hiding from you. So you can't see it from this slide. But it's extra work. You can show it. Okay, last example. This is the work of Alex Watson when he was doing his PhD. So this is a censored stable. So here now what we do is we take a clock which moves like real time, only if the stable process is above the origin. Okay, so this is a new clock, and I take the inverse of that clock. So that clock only ticks when the stable process is above the origin. It stops ticking when the stable process goes negative. Starts ticking again here. stops ticking, starts ticking. So the clock is only ticking during these times. So what I do is I make the inverse of this. Oops. Shit. Oh, crap. I make the inverse of this clock and subordinate the stable process by the inverse. All that's doing is shunting, in a different way, is shunting the path up. It's just moving the path up. Okay? Just shifting it across. So you're introducing a new discontinuity, which is kind of where I left and then came back in. All right? So the resulting path, of course, is a nice, there has no great big gaps in it like that. Again, it might be an exercise, it's not, I don't think it is. You can check that this transformation preserves self-similarity. So before we only worked with the minimum and x, now I'm suggesting that I use the scaling property of x through this time change and its inverse to verify that this is a self-similar Markov process. I've added this extra indicator to say, well, just keep shunting across until you hit the origin, because for some stable processes, when alpha is bigger than 1, you remember that we will eventually hit the origin. So eventually we'll cross up and down, and we'll accumulate to the origin. And then off it will go again and do other things. So in that case, I'm just going to stop the story right here. Okay? When alpha is less than 1 or equal to 1, it never touches the origin. So this is not a concern, it runs forever. But when alpha is bigger than 1, it will accumulate to the origin, it will hit the origin. So my centered process would go down to the origin and apparently come out again of the origin. But I'm only dealing, remember, with positive self-similar processes until they hit the origin, because that's where the Lamperti transformation is. So this guy, again, a bit like my previous hint, there's something similar going on here to what I mentioned before. It's behaving just like this self-similar process, so the one which is just killed when it goes negative. The first bit of path is behaving the same way, whereas before I kill it, I reintroduce it at a different point. And then it behaves in the same, I kill it, and then I reintroduce it at a different point. So this stretch of path here is essentially moving like another stable process. Given the re-entry point, it continues as a stable process. So it means that surely, I mean, when are these reintroductions happening on the time scale of the underlying Levy process? So before, when we considered the kill Levy process, the kill stable process, this was happening at an exponential time on the time scale of the underlying Lamperti-Levy process. So I'm reintroducing after an independent exponential. And then I'm repeating. So it means what I'm doing is the underlying Levy process to this object. So this guy should be the one associated with the killed stable, but we've stripped off killing. And instead of killing it, we introduce it back into the game at an exponential time, but with a discontinuity. So it looks to me like it's adding a compound Poisson process. So every exponential time, it regenerates rather than killed, right? Okay, so there's some work to do there, but again, fundamentally, this guy is our basis on which to start calculating. We need to work out this compound Poisson, and it comes out amazingly again as a hypergeometric, a different one. They all look the same, but they're very different. They're all different, the constants.
Amazingly, it took like 4 months to complete.
well, yeah.
Magic.
And then here's another exercise which I think you can do today or by tomorrow at least. So take this is Jose Luis's result with Juan Carlos, half of it. So take a symmetric process, and we said that a symmetric process, when you take the modulus, is a self-similar Markov process. The modulus makes it positive, so it's positive self-similar Markov process. It has this representation. What's the psi? I'm saying it's this. So this is worked out by Juan Carlos and Jose Luis for alpha less than 1, but later for alpha bigger than 1. It's actually the same identity. And now you see we're getting these weird halves appearing, but it's not quite in the hypergeometric class. It's because of this half, but it's derived, it's kind of hypergeometric when you replace z by half z. And again, it's all about this psi star. It's all to do with the psi star, because if you think about the reflected process, if you think about what happens when you reflect, so it's a resurrection after the first passage below the origin. So your stable process would look like this. Now you want to fold up these paths. So you want to reflect this bit of path here. So somehow it ends up here. Okay, and then again over here, you're going to fold it up, you're going to reflect it up. So these are the periods it's normally negative. Symmetry is important. That's saying it's the same thing when you reflect it. This wouldn't be a Markov process if this were not symmetric, because when you reflect it, this thing would somehow be changing its characteristics from this thing. It wouldn't be continuing in the same way. So essentially, life starts the same as this one, again until this time which we know is exponential q star for psi star, right? Not for x, but for psi star. Remember, x has a time change attached to it. The time change is the psi star, but as far as chi star is concerned in its endogenous time scale, this jump down is an exponential with this q star that we've worked out. And then instead of ending there, we bring it back in at a different point. So it's another compound Poisson that we're adding to the system. Instead of killing it at an exponential, we're adding a discontinuity to the psi and progressing things along, and then another exponential would normally kill it, but we reintroduce a discontinuity and we continue it. So this guy is also somehow the representation of the reflected process of this mod x. So the Levy process associated to that must somehow, so if we look at its, it must somehow start by being psi star theta, take away the killing, and then there's some compound Poisson jump structure that needs adding to it. Okay? And that's how you would get to the answer over there. Again, if you fiddle around in chapter 8 in my book, I think it's clear that all of these discontinuities in all of these examples are to do with overshoots and undershoots. The place of re-entry depends on where you left and where you went to. Okay? I've practically done the big problem for you by telling you that. All right, so I think I'm going to stop there, and then you can carry on tomorrow. So in terms of exercises for today, I've only got a semi-hard one and an ultra-hard one. So I'm not expecting any answers this afternoon, but you probably worked out by now that very similar questions. There's something very similar about them. Okay? So for the rest of the week, try this. And this one. With the hint. And don't ask Jose Luis how he did it. Okay. Questions? Osvaldo.
I don't remember well if Bertrand's construction of a condition to stay positive Levy process is the same as the shunted process.
So Bertrand's.
What's the difference? No, the sensor stable process, I think it's the same, and the condition to stay positive Levy process.
No,
What's the difference?
very slightly different. Very slightly different. Bertrand's construction of condition to stay positive is that's actually another way to prove the process condition to stay positive is to find its Levy its hidden Levy by doing what you just suggested, by analyzing Bertrand's construction. Bertrand takes the process here. Oh, Jesus. He takes the process here and he glues it there. So my censored process shifted across there, and my resurrected process, the variants of the resurrected, I either flip it up or, yeah. So they're all variants on the same theme.
Okay, and the underlying Levy process for the post-infimum and pre-infimum has been calculated because it's like the condition to stay positive. But because we know jointly the law of the pre-infimum and
Yeah.
post-infimum, is it known that the hidden Levy process
The post-infimum, the pre-infimum, so the pre-infimum just gives you the law of the Levy process condition to hit a threshold, and then you glue on a version of the condition process started at 0 from that point, right? So I think you're asking me, what does that tell us about the underlying?
Yeah, and if it is known for the both the variant Levy process, because we know the law of the pre-infimum and the post-infimum, the bivariate law.
Oh, you mean whether it tells us something about the Xi, the pre and post infimum of the Xi? Yeah, it should do. Yeah. Yeah, because I mean, for example, the point of the global infimum of the condition process is a point in the range. I mean, it's the absolute infimum of the underlying Levy process. And in fact, I think that's another way you can deduce the Wiener this hypergeometric shape of the exponent by actually using what you've just said to calculate the global. You take the global infimum of the condition process, and that must be e to the power the global infimum of the underlying Lamperti Levy. So you know the law of the one, so it gives you the law of the other. When you have the law of the other, you essentially have the one of the two Wiener Hop factors in the hypergeometric expression. So that's one way to get the. In fact, I think this is how I do it in my book. Now I'm remembering. But you're absolutely right. So so the moral of the story is, any path transformation you have some handle on for the stable process, it goes back into something about an underlying Levy process, depending on what you've done to it, and vice versa. Anything about the underlying Levy process which you can deduce tells you something back about the path transformation of the stable process that it represents. So it's a game of tennis. And in fact, this is exactly how you calculate all these things.
So being stable, if we have the path transformation and we have the path formation for the condition to stay positive and that stuff.
The what transformation? Sorry,
The condition to stay positive and
bath transformation, did you say?
Yeah.
Bath?
Path.
What's the bath transformation?
Path.
Path, okay, right, okay. Sorry.
So we have those. Why we need to be stable? Just to explicitly calculate, or why?
Yeah, because we're calculating these exponents by virtue of the fact we know what the stable process is doing. Now, as far as I know, can you think of, so remember there's x and there's psi. X is the self-similar, psi is the Levy. So how many x's do you know in explicit detail? So the only ones that I know, as far as this course is concerned, are things derived from the path of Brownian motion or things derived from the path of a stable, because those processes are self-similar, plus they're also Levy processes. But are there any other self-similar Markov processes which we could put on the left-hand side here? I don't know any, other than playing around with the class of path-perturbed stables. I'm not sure I could think of any. However, I should say that these path-perturbed stables, they keep coming up. They come up again and again and again in the literature. They appear in fragmentations. They appear in planar maps. And Juan Carlos tells me to shut up now. So I have to stop. Okay.